we'll just look at some of the buildings. So this is a very special shaped building, and so this is what we call clear point. And in this particular building, there were large cantilevers, like this beam cantilever is about over 4 meters, and how all that is made possible is by using pre-stressed concrete. So the tendons of the beam starts somewhere here on the other side of the wall, and these all kept there using this pre-stressing. So this is the Sky Garden building, and this is a Fairmount building. And in this particular building, the building actually turns by 45 degrees at the top of the car park. And this is Cascade Monarch. And in this particular building, originally it was planned as an office building, and they constructed only the first 3 or 4 floors, didn't construct the tower, but later they thought it's better to have an apartment building. So all these columns were strengthened, and then the apartment tower came on top of the strengthened columns. So this is a model of that particular building. And here you see that, at this level you get car parks and shopping complex and all that. Above that you get a tower, which is used as apartment building. So if you look at a building like this, in the top part you get shear walls, columns, slabs and all that. Then sometimes what you find is the requirement of the car parking will not allow you to continue all these structural elements to the ground level. So which means you have to now change the building. So to make this change possible, we use what we call a transfer plate. And using a transfer plate, it's possible to transfer the loads from above to few columns below. And then these columns also have to be supported. And the columns can be supported using the pile caps. And if you want, you can even model the piles as well. So the vertical load resisting system. So in a tall building, you get 2 systems. One is the vertical load resisting system. The other one is the lateral load resisting system. So sometimes one can serve both as well. So if you look at the basic vertical load resisting system, it will consist of columns, walls, pile caps, piles. And if you look at the size of the columns, they will not be the usual small columns. They will be massive columns of the size of something like 1 meter by 1 meter. And sometimes to make sure that you can do the car parking easily, we go with elongated columns, something like 0.6 meter by 1.4 meter. And when you consider the concrete walls, the minimum thickness is about 200 millimeter, but 225 and 250 are a bit easier to cast. And 250 is actually can be cast easily, whereas 200 needs little extra effort in casting. And anything above 250 can be constructed very easily. And so On the other hand, one of the new additions to the system is called diagrids, and it's a kind of a diagonal arrangement of vertical members, so that it can actually help in resisting lateral loads as well as vertical loads. So what is used in Altea building is a diagrid arrangement. So if I go up, so in this particular building you can see the diagonal arrangement, which is called a diagrid. So this is a diagonal arrangement and it's called a diagrid. And these verticals will allow the loads to be transferred. And if you look at this, you can see these diagonals are double height. That means, within one diagonal, you get two floors. If you have a closer look, you will see that, within one V shape member, you get two floors. So, and the middle floor is actually connected only, and it is, and every other floor, you get a proper connection between the diagrid and the flow, whereas the intermediate flow is just connected to the diagrid system. So that's a new addition to the structural systems that you can use. So basically the wall thicknesses 200 millimeters is the minimum. And when it comes to reinforcement in the columns, generally, 0.4% is the minimum in columns, whereas in the walls, the minimum can be 0.4%, but when you are using Eurocode, they allow you to go down to 0.2%. But what actually happens is in the lower floors, most of these vertical members, walls, columns, all will be fully loaded. So you'll find that usually you need about 1 to 1.5% reinforcement. Sometimes you can have columns which are having about 2 to 3% reinforcement as well. Then when you have walls having with more than 2% vertical reinforcement, then you have to actually make sure those reinforcement is properly restrained. Otherwise, in a wall, you can simply have vertical bars, horizontal bars, and some linking bars, but these need not satisfy the link requirement for columns. The link requirement for columns is, generally we have a general rule, something like, the link spacing can vary between 8 times diameters to 20 times diameters. And early in the British codes, we used to limit it to 12 times diameters of the largest, of the smallest vertical bar. So these all to make sure that, when the column is heavily reinforced, which means the column reinforcement will be in compression and the reinforcement will not buckle. To prevent buckling of the reinforcement, you need to have a certain restraint for the reinforcement. So, but in the case of columns, you will find that we have columns. In case of earthquakes, always the hinges will form somewhere here, and hinges will form somewhere here. So because of that, we can have closely spaced links in these areas. Something like 125 center to center could be common in this area, but other areas you can go for something like 12 times diameters to 20 times diameters. And I generally prefer something like 8 to 12 times diameters for the links in the column. So, whereas at the top of the column and at the bottom of the column, you can have extra links, and that is the reason is that's where you can get plastic hinges formed. So if you detail a tall building properly, uh, what actually happens in an earthquake is during the earthquake periods are very low. So that means the earthquake is the earthquake waves change the direction very fast. So if you look at the frequency of the earthquake and the frequency of the smaller buildings, you will find that frequency of the smaller buildings are pretty close to the frequency of the earthquake, and because of that reason you can get amplifications. Whereas in the case of large buildings, it might take about 4 seconds to complete one cycle. So the natural period of vibration may be about 4 seconds. So whereas the earthquake changes very rapidly. So by the time the building responds to the earthquake, you will find that earthquake has almost over. So you will find the big building, large building will complete only about 3 to 4 cycles before the earthquake, which may be lasting only about 15 to 20 seconds, uh, completes. So because of that reason, you will find that most of the time the large tall buildings are safer in earthquakes in than the smaller buildings. So generally, large buildings are safer in earthquakes. So to make sure the building remains safe, you have to take some precautions. And actually, the main precaution you take is we'll form, we'll ensure that the concrete is properly confined at the places where the plastic hinges can occur. And as I explained earlier, the plastic hinges generally occur at the floor levels, just above the floor level or below the floor level, and in the beams very close to the column. So in those areas, we ensure that the tall building uh, is provided with adequate confinement, especially for beams and columns. So in addition to that, when it comes to piles, we'll make sure that all the piles are properly uh, connected at the ground level by using ground beams and slabs. And I will come to this particular point in a little later, because it's generally when you are designing beams, we make sure that the span sections of the beams are designed for slightly higher moments that can occur due to various differential shortening that can occur in the tall building. So we'll discuss that point in a moment. So we'll first talk about these transfer beams and transfer plates. So when you have a tall building, one of the requirements in Sri Lankan context is that you have to ensure that car parking requirements are met. So, for example, if you have apartment building where each apartment is less than 200 square meters but greater than 50 square meters, so that means between 50 to 200 square meters, each apartment should be provided with one car parking space. So if you have an apartment building with 200 apartments, then you have to ensure that 200 car parking spaces. And each car park is 4.8 meters by 2.4 meters. So when you look at this particular figure, you will find that in most of these buildings, you will do something like this. Most of these buildings, each car park space is 2.4 meters by 4.8 meters. So you will combine 3 car parking spaces and then provide a column. And here also you will provide a column. So you will find that here you get a column, here you get a column. And the same column will be repeated again after 3 car parking spaces. So you will find that, in the ground level, you might be having a grid spacing of 8 to 8.2 meters, depending on whether these columns are 400 millimeters wide or 600 millimeters wide. The length of the column can be about 1.5 to 2 meters. So you can see you can create very large columns by having a grid spacing like this, where between two grid lines you can park 3 cars. You can park 3 cars. So automatically you will settle for some grid arrangement like this. The other possible arrangement is, instead of having 3, you will go for 2 car parking spaces, and go for this, but it's less likely because then you will end up with a lot of columns. So this is another arrangement. So car parking dictates what you are going to do below the main building level or the tower level. So in the lower floors, you will need a lot of car parking. So a building may have about 3 to 4 floors of car parking. And in those areas, you don't like to have too many columns. So we'll be going for something like this. Makes the column spacing to be in the grid of 7.6 to 8 meters. And actually it can be said that it's about 8 to 8.2 meters. So in addition to this, when you have a car park, you'll need to have the access road. And if you are allowing two-way traffic, then you need 7.3 meters. If you are allowing two-way traffic, then you need 7.3 meters. And generally the access ramps will have a maximum gradient of about 8 degrees. So the car parks are generally arranged on split level to reduce the length of the ramps. And so the idea is, rather than going from one floor to the other, which might involve a climb like 3.2 meters. So when you have 2 floors, you will arrange one set of car parks here, other here, the other one here. So when you are moving from one level to the other, what you need to travel is only 1.5 meters, so whatever the half the floor to floor height. But in car parking floors, generally we keep the floor to floor height somewhere around 2.6 to 2.8 meters, because greater heights are not necessary. The height of a vehicle is about 2.1 meters maximum. So in the car park areas, you can have heights between 2.4 and above. So to allow for structural elements and so on, you might end up with something like 2.6 to 2.8 meters for the car park areas. So if you look at the grid of apartments and hotels that you are going to get above, the grid arrangement can be very different to car parks. But in the case of commercial buildings, sometimes you might be able to retain the same grid arrangement, but not in hotels and apartment buildings. So generally in the apartment buildings and even in hotel buildings, you'll find that the grid spacing of about 5 meters is preferred. Grid spacing in the range of 5 meters is preferred. The reason is, in apartment buildings, we don't like to have a very large floor to floor height. We like the floor to floor height of the apartment building to be reduced so that the overall height of the building can be reduced. And because when the overall height of the building is reduced, we can actually reduce the height of the facade, and in doing so we can save some money. So to keep the beam depths at reasonable value like 500 millimeters in apartment buildings, you will go for something like 4 to 5 meter spacing in the case of apartment floors. So you can see there's a problem. The problem is in the car park area, the grid you need is about 8 to 8.2 meters, whereas in the apartment building, the grid you like is something like 5 meters. So this will actually result in what we call the transfer beams or transfer plate. And so we have to see how these can be dealt with. So if you look at this particular building, it's called Sky Garden building. And in this particular building, the building actually turns by 45 degrees at this level. So basically you need below that is the car park area. So you need fairly deep beams arranged in a grid, fairly deep beams arranged in a grid, so that this will act like a transfer member, where you can see in the upper part of the building is very different to the actual building at the lower part. So in addition, what we have talked is the vertical load resistance system, where we need one set of arrangement above the transfer plate and another set of arrangement below the transfer plate. So now we'll talk about the horizontal load resistance system or the lateral load resistance system, because these tall buildings are subject to very high wind loads. So we have to make sure those loads are resisted without resulting in too high accelerations and movements. So we need a very good lateral load resisting system to resist the wind loads and occasionally earthquake loads as well. Right? Sometimes, although we design the building for earthquakes, an earthquake of significant magnitude might not hit the building throughout its lifespan. But and this is true even for an area having a fairly high incidence of earthquakes. So basically, even if you consider some place like Nepal or Iran, where the earthquakes can happen easily, an earthquake hitting some particular area twice in a short period is very remote. It's very remote. So although we hear that earthquake has occurred in these regions, they will not occur at the same place. They will be, say, a few hundred kilometers apart. So because of that reason, the chance of a building being hit by 2 or 3 earthquakes is very remote. So but still, because earthquakes can cause a lot of damage, we generally tend to take enough precautions in buildings against earthquakes. Then to resist the lateral loads, as we have already learned, we can use concrete walls that we call shear walls. And the next topic we are going to learn after this discussion is what we call coupled shear walls. So that means, when two shear walls are in the same plane, we can connect the two shear walls. For example, if you have one shear wall here, another shear wall here, and it's possible to have a beam connecting the shear walls. So what actually happens is, if there is no connection, then just a pin connection, then all these walls will behave independently. But when you connect it with a beam, then the beam deforms, and at each floor level there's a beam that deforms like this. Originally the beam is horizontal, but due to the deformation of the walls, these will deform. So because of that reason, you will find that this combined system can act together, and that can actually share the bending moments more effectively while reducing the magnitude of the bending moments as well. So I'll show you how all this happens in a moment when we start discussing the next topic. So what actually happens is, these coupled shear wall systems can be much more efficient than the individual shear wall systems. So we'll learn about it so that we can understand how the buildings behave. And then the other option that you have is, instead of individual shear walls, we can have shear walls in assemblies, which we call cores, shear cores. We can have something called shear core. The idea of the shear core is that you will get lifts, and in the shear core also, what we do is we close the door opening that is on one side with a deep beam, so that the whole thing will behave more like a closed box rather than open box. And if you take two cardboard boxes, one is like this, the other one is like this, A and B, and A will be much stronger than B. So what we do is, when you have a situation like B, we connect it with a structural element like a beam, so that it behaves as if it is closed. So that way we can improve the efficiency of the shear core. So that's why you see always, when you have a concrete shaft to accommodate the lift, we always, the spacing above the door is cast with concrete, and you will get the core behaving almost like a closed box. And then now we discuss this particular point. When the number of floors is less than n floors, we can assume that the shear wall will carry all the lateral loads. So last time I did not have this facility, so I'll just discuss that point. And so when you have a building, there can be few frames like this, and you might have the lift core, something like that. Generally we prefer this to be in the center, but for the time being we'll assume it's something like this. And provided that we do something to balance the wall, so that this way, when the wind loads are acting, the building does not twist. This way, when the wind loads are acting, again, you can see this length are the same. So again, the wall structure will not twist. If you can arrange the structure this way, then we can say all lateral loads are taken by shear walls and all the vertical loads by the frame. So what you have to do is, when you are designing the frame is like this. So you get supports. So when you are designing the frame, at a particular floor level, you will consider a simplified subframe like this. You will consider simplified subframe like this. Then you will apply pattern loading. So first you will apply 1.35 GK plus 1.5 QK, and then you will go for pattern loading like this. This again 1.35 and 1.5. Here you get 1.35, and you will go for another pattern like this, and then you can get a bending moment envelope, and you can do the design. Get an envelope. Then you can do the design. And in addition to that, because the frame columns are not carrying any lateral loads, you can find the bending moment in the columns also by using a simplified subframe like this. So although the building is having 10 floors, you are not going to analyze all 10 floors. You will select one of the floors and then do a simplified subframe like this, and then perform the analysis to get the bending moments that you need to use for design. And when it comes to the lateral loads, you take the shear walls and say they are all subjected to lateral loads and design it as a cantilever. And the special feature of cantilever is statically determinate. Statically determinate. So the bending moment at any height, the load is W at any height X, the overall height is H. The bending moment is given by W H minus X squared divided by 2. That is W times H minus X will give the centroid, and then H minus X by 2 will give the distance to the centroid. So the bending moment is equal to the force multiplied by lever arm. So you will get the bending moment at any level as W times H minus X over 2, X squared divided by 2, which means the structure can be analyzed without using the computer. You can simply analyze the structure without using the computer. So that's the advantage of using this particular assumption that all the lateral loads are carried by the frame. All the lateral loads are carried by the walls, and the frames will carry only the vertical loads. So the designs can be done easily with simplified methods. So we'll share the screen. Okay. So what happens above the 15 floors is what we have learned already, and that is the wall will become flexible above the certain height, like about 10 floors, the wall will be more flexible. And the frame, and we have learned this already, cantilever mode and the shear mode. And as a result of this interaction, we'll get some deformation like this. we get a deformation like this in the actual building. So that is considering the wall and frame interaction together, and we need to go for proper 2D or 3D modeling, and then outriggers, bearing beams, tubular structures, or any of those can be used when the structure is tall. And this actually shows a kind of a reasonable heights for different systems: rigid frame, frame and shear, and then belt trusses, frame tubes. So all different types of systems. And on internet, you can download this type of things easily for different systems. So when we move away from the general boundary of about 10 floors, we have to think seriously about how to generate a model of the building. How to generate a model of the building. So if I show you some example, we looked at this particular model, and so you can see you have to create a mathematical model of the structure, and the mathematical model need not be exactly the same like the actual model, actual structure. So it can be slightly different. So you have to create a mathematical model. So tall buildings are complicated structures. So you have to actually come up with a simplified mathematical model to do the structural analysis. And so you can use general purpose programs like SAP 2000 or programs specifically made for buildings like ETABS, MIDAS, GEND. And certain programs are stronger in certain aspects. So MIDAS GEN is said to be stronger with axial shortening effects. So what we need to do is, when you have a building, first create a mathematical model on paper, and then use those data to create the computer-based mathematical model. So the first thing is to create the mathematical model, and to create the mathematical model of the actual structure, you have to find the member sizes for the structure. So once you find the member sizes for columns, beams, slabs, and so on, then we can start guessing the type of answers we should be getting by doing simple hand calculations. So once you make the mathematical model, you can verify whether you are in the range closer to the, whether you are in the range closer to the what you call the answers given by mathematical model. Sorry, answers given by manual calculations. So in that way, you can ensure that you do not have major errors in the computer model. So if you are getting something reasonable to what you expect, then you know that you are actually in the close range, and then the mathematical model that you created on the computer is a reasonable one. The reason for doing this manual calculation is to make sure that you do not have major errors in the computer model that you make. So basically, one of the basic calculations that you do is, when you have a grid of the building, here the grid of the building on the plan. So this is a plan view. And one of the assumptions that we make is based on the tributary area. So for this particular column, the loads in this area will be transferred to this column, and in the case of edge column, the load on this particular area will be transferred onto this. So this way, we can work out approximately the load that we can expect on the column per flow. And when you know the number of flows, you can see whether the answers that you get from the computer model are reasonable or not. And similarly, even for beams, you will have some idea. The beam moments should be in the range of WS squared over 11 or WS squared over 12. That range, the bending moments in the beam should be in a particular range like that. So this way, you know, you can have some idea about the answers you should be getting from the mathematical model. And then if you are not getting that type of answers, then you can always revisit the mathematical model and see why you are not getting the expected answers. So you need to have some understanding of how to get the answers for the mathematical models approximately by doing manual calculations. So when you do the actual model, you can always verify whether you are in a reasonable range. So these are some of the latest buildings which are fairly tall. So we'll look at some of the fundamentals and applications. So if you take any building, you cannot have a building that is going to move only in one direction. So basically, when you have a building, we expect this is the building. The ideal situation is it will move this way, it will move this way. But what actually happens is, in addition to these two movements, there might be certain amount of twisting in the building as well. So the building will start twisting like this rather than moving. So there can be some twisting in the building. You know, it's not possible to make it zero. So even if you have a building that twists to a certain extent, generally the columns, beams and walls will not be subjected to torsional moments. Then you will ask why. So the reason is, so even if the building twists, if you have two walls like this, the building twists, then there will be a bigger force on this one than on this one. So the forces will be like this. So what actually happens is, if you have three walls like this, four walls, the building is twisting, then what increases is not the twisting moment on the wall. What increases is the lateral load on the wall. So you will find this wall is subjected to a higher force than the wall here, because the building is twisting. So even if the building is twisting, still you will not get torsional moments acting on walls, slabs, walls, beams and columns. So that is one of the things you have to understand. So even if the building moves a little bit, still the individual members will not be subjected to any torsional effects. Then you will ask why this torsional effect is so important. The reason is, most of these concrete elements are very good in carrying axial forces. They are also good in carrying bending moments, but they are not very good in carrying torsional moments. So because of that reason, we like the beams and columns not carrying any torsion. The good news is, even if the building twists a little, we actually should try our best to minimize this twisting. But still, if it twists a little, still the columns and beams will not be subject to torsional moments. Then the next thing you have to understand is, when you have beams, generally the beams resist bending moments about one axis. So basically, when you have a beam, the beam will always bend only in one direction. Right? So when you have a beam loaded, it will bend like this, and the axis of bending will be given by like this. So the axis of bending will be something like that. And generally you don't get beams which are going to bend in two different axes. So generally beams will always bend only about one axis. That's a general rule. And there could be exceptions, but you have to look for it. And generally the shear also will be due to this particular bending. So shear will be critical only about one axis. But when it comes to columns can be loaded from two different directions. So columns can be subjected to biaxial bending, but still columns will not be subjected to torsion. So even in a building that twists a little, still the columns will not be subjected to torsion. So when you consider a concrete wall, so when you have a concrete wall, here is a concrete wall, is a wall elevation. So when you look at the plan view, wall is a thin element like this. So this type of walls are very good in carrying loads like this, because it's, if you take the second mode of area about the axis of bending, so I value is given by 1/12 b h squared. So you can see I value is very high. So this wall is very good in carrying lateral loads. But how about, so if you look at this from the elevation, it will look like this. How about out of plane effects? A moment like that, yeah, it's not good. It can buckle easily because it's a very thin member. So the concrete wall is very good in carrying in plane loads. These are out of plane loads. The wall is not very good. The wall is not very efficient. So we should try and minimize the moments transferred onto the wall. And how we achieve this is, generally when you have a wall, and if you want to minimize the bending moments transferred onto the wall due to a concrete slab supported by the wall, what you do is at the beam column junction, you will provide some reinforcement at the top. But for the analysis of the slab, you will consider it as pinned. And general rule is we limit the length of the top bar only to about 45 times diameters from the face of the wall. So when you do this, there will not be sufficient anchorage length and continuity of reinforcement to generate a hogging moment here. And if you generate a hogging moment at this junction, then the wall can be subjected to a high bending moment, and that can actually cause additional problems. But still, when you are designing, because there will be an axial load, generally we consider that this axial load can act with the eccentricity of 20 millimeters. an eccentricity of 20 millimeters. When you are designing the wall. So, and this is due to accidental eccentricities. So that means due to construction tolerances, variations, you can have little bit of eccentricity for the loads. So we generally consider minimum eccentricity of 20 millimeters for the axial load, so that it will generate an out of plane bending moment, and we can check the shear wall for this out of plane bending moment as well. So that is to ensure that the shear wall has adequate capacity in both flexure and vertical load, the axial load and flexure, in addition to resisting in-plane loads. So when it comes to in-plane loads, what actually happens is the wall will this, there will be N and M. So you will get, if you want, you can consider this wall as 1 with 2 ends ons. Then you can find N over BH, M over BH squared, and then you can find the reinforcement that you need by using the interaction chart as we discussed last time. On the other hand, so this is one method. The other method is, if the axial loads are sufficiently large, you can consider that it will be due to two different systems like this. This N over BH, this M over Z, so that you can end up with an arrangement like this. So this N over H, BH minus M over Z. On this side you get N over BH plus M over Z. So that type of arrangement can be sorted out. And when you are designing also, you will consider 1 meter length here, and consider all this will be acting over a column wall of 1 meter length. And for this, you can actually calculate the corresponding bending moment as well, out of plane bending moment. Then what you do is you will go for N over BH and M over BH squared not about this axis. Here we are considering it about this particular axis. But when you are designing this, we consider 1 meter length and design as a column subjected to an axial load N and M, where M is about this axis. So this way we can find the reinforcement required to carry the in-plane axial force and the out-of-plane moment. In-plane axial load plus the out-of-plane moment. So this way we can design the reinforcement in the wall. So there are two ways of designing a reinforcement in the wall. One method is consider it as a column and go with the column interaction chart as we discussed last time. The other method is to consider that it behaves like this one, in the elastic range, and find the stress distribution, and then find the corresponding additional moment and consider 1 meter length and decide the reinforcement on 1 meter length basis, so that you can work out the total amount of reinforcement that you need. But generally when you are doing this, you will not go beyond the midpoint, because the reason is when the wind is acting this way, the wind can act this way also. So there's no point in detailing the wall this side, because when the wind reverses, what has happened here will happen on this side. So what we do is we'll do the calculations only up to the midpoint and select the reinforcement requirement in the wall. So those are two different methods of designing a concrete wall. So either design it as a column or else design it as a uncracked section subjected to axial load and bending moment. So both these methods are acceptable to most of the design standards. So and generally slabs will carry loads in flexure and can act as rigid diaphragms to ensure the deflection at a given flow will represent a global translation and rotation. So basically this is what we call rigid diaphragm effect. So the slab will act like a rigid diaphragm so that you cannot have deformations within a flow. So all the deformations that occur at a particular flow level can be related to the lateral deformation and the rotation. The reason is slab is going to act like a rigid diaphragm. That means slab is not going to deform on its own plane. So those are the things, and there are many more things to be discussed.